As NASA's cosmic online portals blink out and terrestrial scopes get swamped by solar glare, the third verified visitor from beyond our stars, 3I/Atlas, hurtles by Mars at a distance of 30 million kilometers. It's the pinnacle of astronomical paradox. Right when this odd, verdant luminous wanderer reaches its nearest point, the U.S. scientific data streams fade to black. Solely the Martian satellites from Europe, China, and the UAE get the chance to grab this opportunity, snapping the crispest visuals and measurements that our planet can access, all before 3I/Atlas slips away for good. Yet with global top-tier gear shifting amid the urgency, what secrets might the red planet's vantage reveal about this enigma that bucks every comet convention? Time is running out on this extraterrestrial brush. Come October 3rd, 2025, the layout of the solar system bars Earth from participating. While 3I/Atlas glides within 0.2 astronomical units, roughly 30 million kilometers, of Mars, the Sun blocks the line of sight straight between us and the intruder. From our world's angle, the separation in the sky between the Sun and 3I/Atlas narrows to less than 10 degrees. That's a firm barrier for Earth-bound observatories. The majority of facilities won't endanger their lenses or detectors when an object drops under 15 degrees from the Sun. Heading into early October, the intruder's spot sinks deep into that risky area. Not merely for an evening or so, but across almost 6 weeks, from the end of September into the start of November. Mars, though, holds a position in its path that's offset by over 40 degrees. The angle formed by the Sun, 3I/Atlas, and Mars on October 3rd stands wide, frequently exceeding 50 degrees. Thus, the probes and landers around Mars enjoy a pristine, glare-free outlook, as all terrestrial gazes get overwhelmed by the Sun's brightness. The figures paint the picture clearly. During the peak proximity, our planet's sight line is obstructed, but Mars claims the prime viewing spot. Whatever shift, eruption, or oddity emerges in 3I/Atlas's actions over this interval will register initially, or exclusively, via the devices orbiting or roving the dusty world. For this fleeting period, the fourth rock turns into the system's sole sentinel. Every moment wasted translates to an irreversible blank in the archive. The slot for observations from Mars' side isn't counted in weeks or days. Rather, it's just a few loops around the planet, a narrow opportunity before the visitor accelerates onward and the alignments shift once more. Controllers, who normally plot out meticulous timelines months in advance, must now adapt on the fly. Routine guidelines yield to urgent redirects. Tools built to probe Martian craters or test the sparse atmosphere get redirected toward the void. Systems tuned for steady, incremental research face a rush of unprocessed signals and preliminary snapshots, aiming to snag any surge or irregularity prior to its disappearance. The intensity never lets up. Each overhead traverse or data transmission could mark the final shot at spotting a fresh detail or unexpected burst. No room exists for red tape or hesitation. Success rides entirely on the agility and responsiveness of the crews managing those far-off probes. The red planet falls under surveillance from various satellites, each tuned to a unique band of the spectrum and overseen by its distinct operations group. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter have locked in frequent imaging sessions for the October 3rd week. Mars Express deploys its detailed stereo imager and Omega analyzer to grab images across multiple colors and probe compositional clues from visible light through infrared. The Trace Gas Orbiter uses its Nomad and ACS analyzers to break down the object's glow into myriad spectral lines, hunting elusive vapors and compound fingerprints. Each can swing from Mars to follow the intruder, though every adjustment weighs against heat limits and operational safeguards. Preliminary results might surface in days, yet comprehensive datasets for the public often arrive months down the line following checks and refinements. The UAE's HOPE probe offers another angle. Its XS Imager and EMU's ultraviolet tool, typically aimed at air studies, can shift to surveil luminous targets against the Martian backdrop. HOPE's broad path and adaptable orientation position it ideally for expansive views and UV readings, particularly should its experts greenlight a fast-track effort. In previous flybys and solar disturbances, Hope has shared refined outputs in under a week if the findings merited it. China's Tianwen-1, outfitted with fine and coarse-scale cameras plus a mineralogical analyzer, might supply backdrop shots and near-infrared profiles upon redirection. While formal word on a 3i/Atlas initiative awaits, Tianwen-1's outputs usually reach openness via organized drops or journal articles, potentially weeks or months post-acquisition. NASA's Mars Reconnaissance Orbiter, featuring the HiRISE camera and XRISM mapper, boasts prior successes in tracking comets and rocks. Pointing adjustments hinge on cleared schedules and vehicle integrity. The ongoing U.S. administration halt further hinders timely sharing of fresh observations. Even if the Mars Reconnaissance Orbiter, MRO, picks up data, internal groups keep watch over the probe's status and measures to safeguard the planet. Outside of Mars, the European Space Agency's JUICE probe plans to try spotting the 3i/Atlas during its journey outward in early November. The viewing conditions aren't ideal, and tools like JANUS, MAZE, and UVS are optimized for remote, dim objects. Whatever observations JUICE makes will endure a lengthy data transmission backlog, with no public sharing anticipated before early 2026. Still, even limited spectral readings or snapshots might assist in following the comet's behavior as it swings around the Sun. This setup creates a multi-tiered strategy, where every spacecraft adds its own perspective and wavelength coverage. Certain findings will emerge quickly, in mere days, while others require months of checking. The phased data drops and collaboration across organizations mean the tale of 3i/Atlas will reveal itself gradually. Every batch of information could serve as a key insight. 9 minutes. That's how long the Perseverance rover kept its unwavering focus on the Martian atmosphere on October 2nd. Every shot from the right Mastcam-Z carries an exact UTC time mark plus details like exposure duration, filter used, and camera angle. The series was meant for atmospheric studies, yet this instance reveals a streak. It slices through the star paths, not lining up with recognized satellites or the gradual shift of planets. The initial process involves adjustment. Unprocessed photos go through a processing chain, with flat fielding, dark frame removal, and fixes for faulty pixels. All anomalies, cosmic rays, every stray reflection, get tracked and dismissed. The Mastcam-Z adjustment routine is routine for the experts. They examine the atmospheric backdrop, verify light measurements, and synchronize the images. It's only after that the streak becomes prominent, a dim, swift streak appearing steadily across exposures. Positioning analysis follows. Experts retrieve the SPICE data files, NASA's system for converting the rover's aim into celestial positions. The forecasted route of 3i/Atlas, calculated from JPL Horizon's orbital data, gets superimposed on the photo collection. The streak's direction and pace measure close to 400 arcseconds, aligning with the comet's anticipated movement from Jezero crater at that time. The alignment fits, the velocity matches, yet chance alone doesn't prove it. Potential errors need exclusion. Cosmic rays typically produce pinpoint single-pixel marks, not extended lines spanning several frames. Lens flares or internal echoes shift with camera motion, but this mark remains fixed. Image handlers use median smoothing and outlier removal to filter fleeting features. Each possibility gets assessed for intensity, scanned for bursts or dimming that might indicate equipment issues or local dust. Light measurement comes afterward. The mark is subtle yet steady. Its illumination, gauged along its path, corresponds to the glow from a hazy, rapid coma at Mars range. The brightness profile stays even, no peaks, no abrupt declines. Researchers match this against simulations of comet flares and sun glints. No irregularities show up. The ultimate check is alignment. The mark's location gets charted versus the orbital forecast for 3i/Atlas. The discrepancies between predicted and actual spots stay under a few arcseconds, comfortably within the tolerance. From such a remove, the proof builds, though formal approval remains pending. The U.S. government closure has left JPL's device overseers quiet. Their evaluation paused. Outside experts like Simeon Schmaus shared their results, but full validation hinges on NASA's approval. The implications loom large. Should this trace prove genuine, it marks the initial surface-based sighting of an interstellar visitor from an alien world, yet research insists on thoroughness. Every phase, adjustment, positioning, light analysis, error checks, must endure examination until the MASTCAM-Z group at Arizona State and JPL chime in. The field awaits anxiously. The trace lingers, etched into 9 minutes of Martian heavens. Its status as a breakthrough or a lesson in caution rests on future developments. On September 25th, one backyard telescope in Namibia provided the final sharp image of 3I/Atlas before Earth's observing slots closed. Snapped from southern hemisphere's mere hours prior to the comet entering solar alignment, the photo showed a green-tinged envelope extending almost 700,000 kilometers wide, roughly double the Earth-Moon separation. The nucleus shone emerald, a shade uncommon among inner solar system visitors. Sun rays passing through vapors rich in diatomic carbon and similar compounds dispersed to yield a striking, almost eerie tint. Yet the form was odder. Rather than the classic elongated dust train seen in standard comets, 3I/Atlas sported a forward-pointing anti-tail, a broad slice of debris aimed sunward, not trailing. This trait, formed by sizable, sluggish particles and the odd angle of its extrasolar trajectory, rendered the comet resembling a floating sail more than a standard streaker. Faint ionic streaks extended from the core, with subdued shells and curves expanding outward, indicating discrete layers or bursts of material rather than a continuous windswept flow. Additional image sequences captured on September 27th and October 2nd, despite increased noise and interference from brightness, verified this configuration. The comet's coma retained its outline, persisting even as the body dimmed, defying the blurring and stretching typical of a dust-propelled tail. Every subsequent exposure strengthened the impression that this wasn't a conventional comet, but rather an entity governed by unconventional principles, an intruder following its unique mechanisms. These images, gathered in the final moments before Earth's observational blackout, now form the foundation for all forthcoming views from Mars. The metrics for 3I/Atlas fail to align with known behaviors. Consider the speed first. Typical long-period comets enter the solar system sluggishly at 20 to 30 kilometers per second. This one shows no deceleration. It hurtles by Mars at close to 60 kilometers per second, and as it approaches perihelion late in October, simulations forecast a peak of 68 kilometers per second. Such velocity surpasses even the swiftest comets in our solar system. The path is equally peculiar. Rather than diving in from a sharp, unpredictable inclination, 3I/Atlas closely follows the ecliptic. Its tilt deviates by just a handful of degrees from the planetary plane. For an authentic interstellar object, that's an uncommon occurrence. Interlopers are generally anticipated from elevated trajectories, not gliding in subtly along the solar system's main thoroughfare. Dimensions present another enigma. Initial luminosity assessments, combined with coma simulations, suggest a core spanning at least 5 kilometers, perhaps larger. This ranks it with the biggest interstellar objects detected, comparable to 2I/Borisov and far exceeding Oumuamua in extent. Yet the coma proves even more perplexing. Lacking a traditional dust trail trailing sunward, it features an expansive, stratified sheath. Polarization analyses suggest nested shells or bows. Each scatters light with slight variations. Absent any extended fibrous tail, it's a vast, organized haze that challenges basic comet dynamics. Both polarimetry and photography underscore the irregularity. The coma's verdant hue, caused by diatomic carbon, is prominent, as is its steadfastness. Despite solar warming and an encounter with a coronal mass ejection, its form remains largely unaltered. The velocity, path angle, dimensions, and coma architecture combine to form a silhouette that strays from comet norms. For those crafting dynamic simulations, every measurement poses a novel hurdle, with standard approaches providing scant guidance. On September 25th, 3I/Atlas faced an alternative trial from a coronal mass ejection launched directly from the Sun. Space weather experts monitored the CME traversing interplanetary voids, anticipating a wave of charged particles and magnetic unrest. For ordinary comets, such as solar outbursts, spells disorder. The abrupt influx of high-energy plasma might erode ions from the coma, spur intense sublimation, and carve fresh tails within hours. Experts in plasma facilities and solar facilities anticipated a classic outcome: a shock wave, a surge of charged gas, or perhaps a noticeable twist in the envelope. Yet the event unfolded subdued as the CME engulfed 3I/Atlas, with Earth-based scopes and Mars-based sensors recording the effects. Rather than a vivid outburst or reconfigured coma, the structure shifted little. The emerald aura remained sharp. The antitail preserved its tapered shape, and peripheral layers displayed no evidence of rapid swelling or breakup. Alterations in form were slight. No evident ion tail emerged, no sudden glow appeared, not even a disturbance across the coma's nested curves. Plasma specialists found this baffling. They had foreseen greater ionization, an inflated sheath, or at minimum, signs of magnetic disruption etched in the glow. The lack of a pronounced response raises uncertainties regarding the body's makeup and inner makeup. Does the coma possess exceptional durability? Or does its makeup inherently withstand solar disturbances? Absent a distinct ion tail or flare of spectral lines, conventional analysis tools fall short. Investigators turn to Mars probe plasma detectors and frequent spectral scans for insights, expecting that amid the unprocessed data streams, traces of that solar event lurk, ready for discovery. The trajectory of 3I/Atlas erases any ambiguity about its provenance. It slices across the solar system along a hyperbolic arc, untethered and outbound forever, a clear signature of extrasolar origins. This alone aligns it with just two prior intruders, 1I/Oumuamua and 2I/Borisov. Yet confirming its roots is merely the entry. The true difficulty lies in naming it and gauging the reliability of categories. Certain scientists opt for the term interstellar comet, invoking the verdant coma, the emissions, the tiered sheath. Others pause, highlighting the absent dust trail, the backward-pointing tail, the remarkably steady formation, and the impressive, nearly machine-like pace. The discussion goes beyond mere labels. It centers on proof and the threshold for bold assertions. Progress in science relies on doubt, on questioning not only what aligns, but what holds up against fresh evidence. The experiences from a prior interstellar object mission are still vivid. Theories proliferated. Guesses outpaced reality. Yet only solid figures stood the test. For 3I/Atlas, each irregularity, each unusual hue, each envelope, each steady nucleus demands scrutiny, not exaggeration. The issue isn't if it might be artificial, but if observations force that conclusion. Absent that, the sole undisputed fact is its origin from beyond our solar system. All other ideas stay speculative, pending the upcoming spectral analysis, the next photo, the following revelation. For those tracking the saga of 3I/Atlas, essential resources include public datasets and crowdsourced reviews. Begin with the spacecraft information hubs. ESA's Planetary Archive, the Emirates Mars UV Center, and the UAE Hope Probe's public repository. These serve as prime spots for preview visuals, wavelength readings, and activity notifications. The ExoMars Trace Gas Orbiter and Mars Express release preliminary outputs in days or weeks, often in Level 1 or 2 data formats, occasionally with low-res JPEG previews. For swift insights, amateur groups like the Minor Planet email list and the Comet Sighting Archive monitor unprocessed files and highlight oddities right away. Confirmation builds step by step. Upon spotting a fresh streak or flare, compare it against orbit forecasts from JPL Horizons or IMCC. Seek corroborating signals in shared datasets from Mars satellites, Earth amateur setups, or even sun-watching telescopes. Enthusiast researchers frequently share comparative montages, light curves, and trajectory models within hours, particularly if agency pipelines face delays from closures or holds on info. To track the shape as 3I/Atlas nears its closest solar point, observe shifts in the envelope's form across updates. Look out for abrupt shifts, layers, curves, or backward tail glow that might indicate new outbursts. The deepest insights emerge from aligning time-stamped raw images from various probes and light bands, rather than relying on finalized announcements. Right now, openness and backups are crucial. Diverse sensors, separate groups, and prompt sharing of unrefined data are vital to spot what could otherwise go unnoticed. On October 3, 2025, 3I/Atlas came within just 30 million kilometers of Mars, as ground telescopes on Earth were obscured by solar alignment and a U.S. government closure. Orbiters around Mars from ESA, the UAE, China, and NASA served as the only observers, gathering info inaccessible from our planet. Initial snapshots verified a verdant envelope spanning over 700,000 kilometers and a swift velocity approaching 60 kilometers per second. Yet crucial puzzles linger. The actual makeup of 3I/Atlas, the cause of its stratified envelope, and the lack of a typical dust trail. Even after brushing a solar coronal mass ejection, anticipated charged effects stayed slight. As global experts sift through their results and gear up for phase data drops, plenty awaits clarification. The verified extrasolar routes of 3I/Atlas face no challenge, but its traits test existing comet theories. With more info on the way, the tale of this outsider stays incomplete, underscoring that despite worldwide tools, certain space enigmas persist. Music.